Okay, everybody, welcome back to another question where we need to use Hooke's law and conservation of energy. Let's read it. We've got a particle of mass 2 kilograms to one end of a light elastic spring with P, natural length 0.8, lambda equals 12. The spring is on a rough plane at 30 degrees to the horizontal. A to B is 0.3. A to C is 1 meter, and the coefficient of friction, mu, is 0.3. We want to find the speed of P when it passes through C. So we're going to let this particle go from B, and the spring will shoot it down a slope. That's our question. First thing you should do once you've read the question is add some key lengths onto your diagram. So for us, we should start with the natural length of the spring. So zoom in a bit. And from A, going down the slope to here, this is 0.8 meters. I'll add that on in a second. And then this extra length here is going to be a 0.2 to C. So I'm going to put here x equals 0.2 meters to get to C. But this main length, L, equals 0.8 meters for our spring. We should also consider this other length on the other side of L, though. So to go from the natural length of the spring back to point B, this length here is going to be an x equals negative 0.5 meters. And that is important for us in this question because it says spring with a P. There is some elastic potential energy when you compress the spring. So negative extension is still important. Next thing I would think about is, what is this question actually asking for? It's asking for a speed later on. And whenever we're thinking about speed, we're thinking about energy, conservation of energy, different types of energy involved. And because our diagram is on a slope, that means we're going to have some gravitational potential energy being exchanged here. So I'm going to add a triangle to help myself. This is a right-angled triangle. Here we can think about the height that our particle has lost or gained as it moves from B to C. So I'm going to add in this length here of a 0.7 meters from B to C. And also I'm going to add in this theta of 30 degrees for our slope. And if you're good at trigonometry, then we know sine 30 is 1/2. So the vertical distance going from C to B will be half of 0.7, so 0.35 meters is that vertical side. So that's the important lengths for our GPE. Next thing I would think about is forces involved in this diagram. So going straight down, we've got an mg for particle of mass m. What is the mass of ours? 2 kilograms. So we're going to have 2g going down. Perpendicular to the plane, we're going to have a reaction force, capital R. And acting parallel to the plane, along the plane, we're going to have friction. And we should be a bit careful about which direction this points. Because our particle is moving from B to C, friction is going to be the opposite of that direction. Friction is going to be trying to stop the particle from moving. And this is going to be mu R, or 0.3 R, using our mu. That's trying to resist the motion of the particle, so it's pointing up the slope. So maybe our first thing then, before we think about any types of energy, we can definitely say something about these forces. And let's actually add in a couple of thetas just to help ourselves on the diagram. So if we know 30 degrees is the angle of the slope, we can also add in a 30 here. And then we can also do one more 30 if we want. From this here, we can add in a 30 from the vertical. Yeah, those will be helpful for us in a second. So our first actual bit of maths to do here is we're going to resolve perpendicular to the slope. So I'm going to consider forces going in this direction. And the reason you should go perpendicular to the slope is then you can take out the r or the mu r from having any effect when you go perpendicular or parallel. So we can say in this direction, r equals 2g cos 30. Yeah, the mu r has no effect looking perpendicular to the slope. So r is 2g cos 30. Well, this is 2g root 3 over 2. So this just simplifies to root 3g. Because r is root 3g. Well, now that means when we're moving down the slope, we also have a value for the friction because we know the reaction force. So we've done a little bit of thinking about forces. Our next step should be to think about energy. So I'm going to go over to my next sheet of paper. And this is our main line of our argument. So we're going to write COE, conservation of energy. And we're going to think about the energy before being equal to the energy after. And by before, I mean the energy when our particle is at B. So let's think about the different types of energy we've got at B. We've got some elastic potential energy. We don't have any kinetic energy because our particle is just still when it's at B. We also have some GPE though. So what I'm going to say is the GPE at C equals 0. Yeah, we can make that choice. That's our baseline. Now we can work out the GPE at B. So the height is 0.35. So this means the energy at B, we've got a GPE plus an elastic potential energy. Our GPE is mass times G times the height, so 0.35. And our elastic potential energy is a half times lambda, which in this question was 12 newtons. So a half times lambda times x squared. If we can go back and check again, x is negative 0.5. So negative 0.5 squared. And the natural length of the spring was 0.8. So GPE plus EPE. And then after, when we were at C, well, we don't have any GPE anymore because C has 0 GPE. But what we do have is we have kinetic energy plus some elastic potential energy still. And we also have some energy that we lost due to the work done. Yeah, and that's the work we did against friction as we were moving down the slope. So our kinetic energy is half times m times v squared. Our elastic potential energy is half times lambda, which was 12. X, when we're at C, is 0.2. So half times 12 times 0.2 squared over L for our spring, which was 0.8. And our work done is the frictional force mu r times by the distance. So we had to do a 0.3 for mu, and r was root 3g, and the distance is 0.7 meters. So going back to here, we've got a root 3g times 0.3 times the distance, maybe I have to squeeze this in here, times 0.7 meters. And actually, if we just zoom out and think for a second, we have lots and lots of numbers in here, and the only thing unknown is the v squared. So this is exactly what we need to do to find the value of v. At this point, it's just quite a lot of calculating then. So 2 times g times 0.35, this should be 7, plus we've got 1/2 times 12 times negative 0.5 squared over 0.8. That gives me 15/8, or 1.875. Half times 2 times v squared, I can do that myself. This just gives us a v squared. The elastic potential after, what have we got? 1/2 times 12 times 0.2 squared over 0.8. I've got 0.3 for our EP afterwards. And our work done against friction, we've got √3g times 0.3, coefficient of friction, times 0.7 as the distance travelled. So I've got 3.637. I'll just do to 3 decimal places. I reckon it will be good enough. √3 times 10 times 0.3 times 0.7. Okay, so we can say here then, this means v squared equals 7 plus 1.875, take away 0.3, take away 3.637. I've got 4.938. And last step, to square root for our v, I've got 2.22 meters per second for the speed at c.